Welcome to lesson 4. This is similar triangles. So first of all, we've been talking about scale diagrams, reductions, enlargements, and then similar polygons. Well, similar triangles have very similar features to similar triangles. Let's take a look. So again, they have to have corresponding angles, so the matching angles must be equal, which is the same with polygons, and the ratios of their side lengths also must be equal. Okay, so the same thing we dealt with, same rules. So first of all, we also have to note that similar triangles, just as similar polygons, must have the same shape, but not always the same size. That's why they're called similar and not congruent. Remember, congruent means they're identical in every way. Let's take a look at an example. So we've got triangle ABC is similar to triangle XYZ. So the minute we're told that it is similar, we know a few things. We know that their angles have to match. So how do we do this? How do we match them up? Well, let's take a look at our few properties we have here. So again, same shape, same angles, same side ratios, but again, different size. So if we were going to match these up, how do you tell which one's the long side, short side, big angle, small angle? Well, when you're matching them up, it's always easiest to find your smallest side. So find your very smallest side on both of them. So on this one, I find my smallest side is XY, and over here I find my smallest side is A to B. So then I would write my side ratios as those ones matching. The other sides that would match, then you could find your very long side. And usually your long side is a diagonal line. And this one here is a diagonal line. It's going to match the other long side, which is a diagonal line. The line that we haven't drawn on is the medium-sized side, and it's going to match as well. So when we're comparing triangles, just like we did with the similar polygons, we must make sure that we match the identical same sides of each of the objects. So let's take a look at an actual example of matching. So again, here it tells us that we have identical angles and they must match. So when we name and match triangles, it's done the exact same way as we did it with the similar polygons. So when naming and matching the triangles, when they are similar, similar means they correspond in every way, we list the angles and sides. That's super important there. We need to list our angles and sides that match. Okay, they have to match. And sides match as long as they're between the same angles. That's, again, super, super important. So the sides match as long as they're between the same angles. So let's take a look at this. Let's match our angles up together here. If we take a look at our first angle on the top left, 43. So 43 is angle Z. If I wanted to match 43, I'm going to match it over here, and I see automatically a 43. They're the angles that are going to match. So I'm going to say angle C here matches angle Z. So if I take a look, I can say angle C matches angle Z. Then if I take a look at angle B is 62 on the small one. Who is 62 on the big one? We find Y is 62 on the big one. So B is going to match angle Y. And we're left with an angle A, which is 75 degrees, who will match angle X. So angle A matches angle X. This helps us when we have to match our sides now. So remember, when we match our sides, they're going to be between the same angles. So if I take a look at the side here, I'm going to take a look at this side here. That side is between 43 and 62. So I need to find the 43 and 62 on the right, on the small triangle. There it is, 43 and 62, and that's the side that's going to match, okay? Because the number, the side length in between those angles always matches. So that means the 7.5 is going to match our 5. So that means side B to C I'm using here at this moment, side BC in the middle here, is going to match side Y to Z. So we can say BC matches Y to Z. If we take a look at the next angle, let's try and start with A. So if I take A to B, for example, on the small one, A to B is between 75 and 62. So now try to find 75 and 62. It is our very bottom leg. So the bottom leg of that triangle is going to match the green leg on the top triangle, the small one, because they're between the same angle. So this is very important to match them up properly. So that means the angle A to B is going to match angles X to Y. Or side XY, pardon me. The last one that we don't have indicated, that one is going to match AC. The last one is between 75 and 43. Again, I find my 75 and 43. And if you find it very, very easy the way I'm doing here and coding it by colors, use your highlighters or markers and code them by colors. It really does help you organize your information. And then it's much easier to solve the questions when you match them up properly. So then we're going to find out that C to A, the blue line, is going to match our other blue line, which is then XZ. Okay? Let's take a look at those. Make sure you have that written down. Take a minute now, pause, and push play when you're ready. Okay, moving on now. If we take a look, just like we did with our similar polygons, we check the side legs, the ones that we just matched up. We check them now to see what their side ratio is. So when I took those sides and I said, okay, well, 4 is going to have to match the 6. Those two short sides are going to match. Well, when they do, I'm going to divide those numbers. Now, when I divide my numbers for all of my ratios, I have to make sure that the same numbers are either all on top or all on the bottom of these triangles. So, for example, A to B comes from my small triangle. So that means I've got small over big. That means for BC and for CA, I need to have small triangle letters over big triangle letters when I match them again. I can't start switching them then and putting big over small. It must stay the same way to compare all three sides. So when I do that, I keep all of my small triangle letters on top. So all of my small triangle sides are the AB, the BC, and the CA. Notice they are all on top. So I've done the matching correctly. So now that I've done that again, I'm going to check my numbers. When I check the ratios, all of them give me the exact same answer, 0.6 repeating. Because they are the same, because they match, this is then a similar set of triangles. Okay, they do correlate. If those three did not match, they are not similar triangles. Again, all three sides of this triangle have to match in ratios. So, if, for example, you've got maybe one side and a second side that match, but let's just say for pretend that this side didn't match. Maybe it was 7 over 9, which would give us 0.7 repeating. Well, we're going to notice that 0.7 repeating is not the same as our other two sides. So if we had a situation like this, even though two sides matched and one didn't, because the one that didn't match, this would not be a similar set of triangles. Okay, so they would not match. Okay, so you would say, no, these are not similar triangles. That is a for instance, but in this case with the numbers we were given, we have a 0.6 repeating, 0.6 repeating, and a 0.6 repeating. So yes, these ones in this situation do match. Okay, take a minute to write that down. Highlight your numbers and your sides, and make sure you have the small over big. The ratios must match, all of them, small over big, small over big, and small over big. If you use this strategy, you will never go wrong when you set up your ratios. Always have the same triangle numbers, always all on top, and then all on the bottom for the other one. Let's take a look at another example. Here's a problem-solving example. It tells us that triangle ABC is similar to triangle GHI. How do I know it's similar? Because it's got this squiggly line. This little squiggle in the middle there, that indicates similarity. So they are similar. They're not equal. Remember we said they're around when we had other numbers like this? Well, in this case, it means they're similar, but not identical. Obviously, they're not identical. They're not the same side. So it wants us to find all of the sides and the angles that are missing that we haven't found yet. And we're going to round to the nearest 10 if we don't know the answers. So, how do we start? Where do we start here to start solving this stuff? Well, here are our steps. We start by labeling our matching angles. Okay? Label the ones that should match. Then our next step is to write the side ratios in fraction form. If we write them in fraction form, again, we need to put small numbers over big, or you can reverse it and put big over small, as long as they all are the same way. So I like doing small over big, so I'm going to put small over big and start writing my matching ratios. So I know that this guy's 40 on top, so this guy will be 40 on the bottom. And I know that all triangles must add up to how much? 180 degrees. So if I know two of the angles, I know this guy down here means 90, and I have a 40 on top, I can easily figure out the missing angles. Those missing angles, I will take 180, subtract my 90, and subtract my 40. That's going to give me 50 degrees for my missing angle. So I know angle H is 50 degrees, and so is angle B. Because remember, if they're similar triangles, which they say they are, that means their angles have to be identical. Let's take a look now at matching our sides. I set up small over big, so now we can match our sides. Remember, if we've got a 90-degree angle, it actually helps us solve it much quicker. Because remember, our legs that touch the 90 degrees, those ones will always match with the other legs that touch the 90 degrees in the smaller triangle. And then the diagonal line, the hypotenuse, will match the other diagonal line. So let's write all the small numbers down. So far I've got a 9, and then I've got, we will label this baby A, and this guy would be baby B. So I've got a 9, and then I've got an A, and I've got a B. Now we're going to find out which sides on the bottom triangle match those ones. So if I take a look at the bottom triangle now, I know that 27 is my diagonal line, so it's going to match the 9. So I'm going to put 27 underneath the 9. And now I'm going to find all of the other missing values. So I've got a 12 on the bottom. So 12 is going to match my other bottom leg here, which I put my A. So that means I'm going to put 12 under the A. Again, how did I find out that that was named baby A? It's because it's across from capital angle A. Remember, the side, we name it, is going to be the small letter of the angle across. Just like baby B is the small letter of angle B across from it. Okay? That's how we find our side lengths. Now, again, we don't know the extra leg. We have no idea how big this guy is, but he has a name. He is across from angle H, so he's baby H. And baby H is going to match our vertical line over here, which matches B. So that's baby H that matches B. Now, we know that we can't solve for values when we've got two unknown numbers. So how can we actually solve these triangles? Well, we take what's called our true ratio. This is called our true ratio because we have a number on top and bottom. Okay, so when you have a complete fraction, number on top and bottom, it's called the true ratio. And this is the one that you use to cross multiply and divide all the time. Now, is it easy for me to find angle A or side H without even having to find what B is? Can I just take this right off and find out what H is? Well, I hope you realize that it's a right triangle, which means I can use Pythagorean theorem. So we can actually use our A squared plus B squared equals C squared to find side H. And then once I find missing side A here, I can do the same thing with my small triangle to find side B. And that's exactly what we're going to do. So I have my true ratio. I don't use the ones where I have values with variables on top and bottom. Remember, we discussed yesterday that we will always be given 3 out of 4 numbers. I take a look. I have 3 out of 4 numbers. 1, 2, 3, and then my missing value, letter A up here that I'm looking for. So, again, we're going to cross multiply and divide. How do we know who to multiply? Again, it's the diagonal numbers. So these ones are diagonal across from each other, and there's 2 digits. We always take the digits that are diagonal. Over here, if I took the other ones, I would have a variable and a digit. I never take one where I have a variable. So I'm going to multiply the diagonal numbers, and you always divide by the number left over. Okay, so give that a try and see what you get for side A. How big is side A? Okay, you have a minute to do your cross multiplying and dividing. I hope you figured out that A is exactly 4. Okay, so now we know A is 4. So I'm just going to redraw these triangles because I have a lot of scribbles on them. So our small triangle now has a 4 and it's got a 9. And I need to find baby B over here. So again, like I said, I'm going to use my Pythagorean theorem. But now, this number here is our long side. That means he's our C value. Okay, he's our C over here, which means I need to subtract. So I'm going to say baby B squared is going to be equal to 9 squared subtract 4 squared. So B squared is equal to 81 minus 16. B squared is equal to, okay, it's going to be equal to 65. Now again, that's B squared. And from our first unit, we know how to take away squared things. We square root them. So if we square root B squared, the squared sign disappears, they cancel out, and I square root 65. So then I find B to be 8.1. Round to 1 decimal place, it tells us to the 10th. So we actually get 8.06, etc. The 6 will round that 0 up to an 8.1. So we found our small triangle. Now we know that this missing side here is 8.1. Now we're going to go to our large triangle. On our large triangle, we had 27 and 12. But we didn't know what h was. We can easily, again, find out how big h is by using the same steps here with our Pythagorean theorem we did with our small triangle. So I'm going to do the exact same thing. H squared equals 27 squared, subtracting 12 squared. Okay, so I gave you a minute to do that. If you take a look, when we subtract those, we're going to get 585. And again, that is h squared. So my very last step, square root the h squared, square root the 585. I'm going to get h equal to 24.186, etc., which rounds to exactly 24.2. Okay? So once you know a little bit about a couple things on these triangles, you can take a look, write your side ratios out like we did over here. Once we have our side ratios, as long as we've got 2 numbers out of 3 on any triangle, like we did in this situation and this one, once we find out the other missing unknown, then we can use our Pythagorean theorem. Any questions so far? This concludes the end of 6.4 similar triangles.